So yeah, thanks for all the talks about dielectric sensing. This is one more of dielectric sensor. So I'm talking about radio frequency dielectric sensor on CMOS platform for detection of Sputum-Mucin viscosity, and this is very critical for things like tuberculosis detection. So it's pretty obvious that during any lung disorder, so the sputum, which is the discharge from the lungs, it the viscosity of it or the content of it changes depending on what kind of disease is present. So, and this viscosity is characterized by the water content of the sputum and also by something called glycoprotein. So, if you can detect this kind of a viscosity really early, so it would be a really early diagnosis of any disorders like bronchitis, for example. And if it can be detected on a full lab on chip platform like this, it would be rapid, it would be low cost, and yeah, it would help in rapid diagnosis and screening of disorders of lungs, for example. So we thought that one way of doing it was using this high frequency or the radio frequency technique on CMOS platform because when you have a CMOS chip, you can easily integrate this with a with a microcontroller and FPGA techniques, and you can have all the microfluidics and everything on top. And this helps in rapid diagnosis of this kind of diseases. So yes, CMOS microwave dielectric sensors was something that we thought we would go for detection of sputum viscosity. So now let's talk about a microwave viscosity sensor. So here we need to understand one thing. Viscosity is basically a mechanical of any material. So it is the elasticity or the viscosity. It defines the mechanical condition of the material. However, we are trying to detect it using microwaves. So we are trying to detect a mechanical property using an electrical technique. So there's a need to understand how we can relate this to these two different domains, the mechanical domain and the electric. And the way I told you was detection of concentration of water. So as I told, the viscosity of the sputum would change, and that would change the concentration of water. So when you change the concentration of water, you're actually playing with the dielectric permittivity of the material, and that's basically you can detect the dielectric change, and that you can relate to the viscosity change of the material. So it's given by a standard Debye equation for this kind of material where you have a characteristic frequency and your overall permittivity is defined by at what frequency you're operating your sensor. So the operating frequency of the sensor will also define the sensitivity. So we need to determine the operating frequency of the sensor where we can detect the change in concentration of water very accurately. Now, if you look at a test example where we have where we have a binary mixture of glycerol and water, let's say. So glycerol is a high viscous fluid. On the other hand, water is a low viscous fluid. Now, let's say we are doing the mixing at 12 gigahertz. This has a very strong slope of the permittivity when you're changing the water fraction in glycerol, because at 12 gigahertz, the permittivity of water is roughly in the range of 45, whereas the permittivity of glycerol is in the range of 8 to 10. So there's a high contrast between the two permittivities, and that's why the sensitivity is very high. On the other hand, if you're trying to do that at 60 gigahertz, for example, that's here, or 50 gigahertz. At this frequency, the permittivity of water tends to is more or less towards 10, and so the contrast is not too high, and that's when you have a very low sensitivity here. And that's the reason we chose our high frequency sensors, or let's say the microwave CMOS sensors, to operate in the range of 5 gigahertz, 15 gigahertz. Now, the sensor design, it's a very typical cross-couple oscillator. So from our circuit design knowledge, we know that you use a varactor here, and changing the voltage in the varactor, you can tune the resonant frequency of this kind of an oscillator. In our case, we don't have a varactor here. We just have the sensor capacitor here. So the sensor capacitor, the capacitance of the sensor changes due to the change of the permittivity of the material on top of it. and that changes the resonant frequency of this kind of an oscillator. So that's what we're trying to do. And this resonant frequency shift will be translated to the change in permittivity, and that we can relate to the change in viscosity. For the sensor, we use a typical interdigitated capacitor, which has, if you just break down, if you just model it, it has three main components of capacitance. One is the fringing fields penetrating into the substrate. The other one is the parallel plate capacitor between the two fingers, and the other one is the fringing field that's coming out on top of it. And this is the fringing field effect that we would try to use. So if you place a material in a test here, this fringing field capacitance will change, and based on the permittivity of the material, and that's what we are trying to detect here. So as I told you, let's understand, we are trying to detect a mechanical property using electrical technique. So you see, for water glycerol mixture, when I'm increasing the viscosity, the resonant frequency increases of the sensor oscillator. The reason is, when you're increasing the concentration of water, your viscosity decreases, but your permittivity increases. And that's the reason the resonant frequency also increased, right? But if you go for another material, let's say ethanol and glycerol mixture, your resonant frequency decreases. However, the viscosity decreases as well, just as was the case of water and glycerol mixture. But at the same time, the permittivity also decreases because ethanol has a lower permittivity compared to water and compared to glycerol as well. That's the reason, although in both the cases the viscosity decreases, in one case the permittivity is increasing, and in the other case the permittivity is decreasing. So this is something which I would address as a clear limitation of the technique, because you really need to know the permittivities of the two contents of the mixture that you're trying to detect, because this can go either which way. So knowing the permittivities is extremely important. So that's why I say that it has to be, when you're trying to use the microwave sensors for viscosity detection, you have to know the permittivities of the material that you're trying to detect. Then we did some tests using different samples from, for example, serum, saliva, Sputum-Mucin clot. So just to see if we can differentiate between different biological samples. And yes, there was a clear difference of the resonant frequency here. For example, saliva has a frequency which is almost close to what we would get if we would just put water, because the water content of saliva is pretty high. On the other hand, this is the pure sputum clot, which is very less content of water and has a resonant frequency of 10.25. And then, yes, with this, we went ahead to do the measurement for sputum content or concentration of water in, or viscosity of sputum, let's say. So as we decrease the concentration of sputum, there's a decrease in the resonant frequency. This is translated to the fact, so when you're decreasing the concentration of sputum, you're basically increasing the concentration of water. So when you're increasing the concentration of water, the dielectric permittivity increases. And as the dielectric permittivity increases, the capacitance increases as well. And that reduces the resonant frequency of the oscillator. And that's what we're trying to detect. So we have a sensitivity roughly in the range of, I would say, 50 megahertz per unit permittivity. So and there's a sharp drop here, and that's because this is around 20% of sputum, and when you go to around 5% of sputum, which means you have a maximum of water there, so there's a huge drop of resonant frequency of the sensor. So this could be ideally used for very early screening of lung diseases, and using this kind of a viscosity sensor, provided we know the permittivities of both the content of the mixture. So in conclusion, what I tried to tell you was, okay, microwave sensors can be used for viscosity sensing, but knowing or choosing the right frequency of operation is very important, which defines the sensitivity. And I showed you how it is possible that the same mixture will be sensitive at 12 gigahertz and not at 50 gigahertz. Then I showed you that, as I told you, that the limitation of the process is that you need to know the permittivities of the two components of the mixture, because In both the cases, the viscosity could go down. However, permittivity could act in two different ways. So knowing the permittivities of the individual constituent is important. And finally, I showed that this kind of an oscillator circuit, where your sensor forms the capacitor for an LC tank, can be used to detect change in permittivity, which can be correlated to the change in viscosity. Yeah, with that, I would like to thank you all for your attention.